Hello, everyone. My name is Michał Trojanowski. I work for Curity, and today I want to talk about something what I like to call military-grade security for APIs, and I will explain why in a second. I think there is no person or no company that builds an API and then thinks, okay, I don't want it to be secure or I don't need it to be secure. Mm, every time we build APIs, we want them to be secure. And it is pretty obvious for industries like finance or medical that deal with sensitive data like money or health data. But there are other industries that can treat the data as sensitive. For example, maybe some government websites and tax-related data, things like that. And in fact, uh, I like to see data in today's world, all data as sensitive data. Because even if you have an API that only shares a list of, for example, usernames and emails, if someone manages to breach your API and steal that data, they might be able to create some more sophisticated attacks against some other websites or some other APIs. So I think we should all think about our data as sensitive data and try to make it more secure. But how do we achieve security? I like to think about it as making the life of the attacker harder. Um, of course, we're never able to make our security 100% bulletproof. There will always be some gaps in our security, but we want to um, we want to make sure that the attacker will have really hard time to penetrate our API, and maybe they will go and attack somebody else. And here comes FAPI. FAPI is a security profile for auth created by the OpenIDE Foundation, and its goal is exactly that. It tries to make the life of the attacker harder, so that it's not simple for them to penetrate your API security. FAPI used to be called financial grade security, financial grade um, security profile for financial grade APIs. But the community that worked on it realized that actually the solutions that they described are also good for any industry, not only financial data. So they actually changed the name. There will be a second version published really soon, and the second version will be called just FAPI security profile, so that it's not automatically associated with financial grade. And this is actually why I like to call it military grade APIs, because whenever someone hears about that they can have a military grade security, then they're interested because everyone wants to have security like the military. But when you hear about finance, then some people think, okay, we don't deal with financial data, so maybe it's not for us. But you should have a look at that profile, because it is a short document that shows you some features and some configuration options that you should use with auth when if your product uses auth or OpenID Connect. Then have a look at FAPI, because it will tell you which configuration options to use and which extensions to use in order to make your APIs more secure. What is important, that security of your APIs is viewed not only from the API's perspective. I mean, sometimes to make your API more secure, you need to make sure that your clients are more secure, or that your authorization server uses some more secure options. We we tend to think about security only, just making sure that no one penetrates the firewall and nobody, gets the data from the database, or is not able to call some remote code directly on our backends. But when we deal with auth, and when we have access tokens and APIs and access tokens that allow access to APIs, and then we don't think about the client security, somebody manages to steal access tokens from the clients, then they will be able to access your API with a legitimate access token and steal some data. And it might be even harder for you to notice that such a breach, because the attacker will use a legitimate access token. So I'll talk about a few solutions that FAPI recommends using. And I want to start with MTLS. MTLS stands for mutual TLS. And so how the classical TLS works, when we have a connection between the client and the server presents a certificate and authenticates the client. So the client knows who the server is. But the server doesn't know anything about the client. And in a mutual TLS scenario, now both parties have to authenticate. So both parties have to present some kind of proof of the identity, for example, in a form of a certificate. And now not only the client knows who the server is, but also the server knows who the client is, exactly knows what client connects to the server, to the API, or to the authorization server. And this technology can be used for something that we call sender constraint tokens. So what are these? When we deal with auth, there are these two types of access tokens. Most of the times, we use bearer tokens in our APIs. But they are not the only type. There's also the sender constraint tokens, which we also sometimes use the name proof of possession tokens. So how the bearer tokens work? When a client is issued an access token by the authorization server, when it sends it to the API will verify the signature of the token and the claims in it. So it will check whether the token is expired or not, maybe verify some claims, for example, the scope of the token. And if the token is okay, the gateway can forward it to API, then the API can verify the token. But if another client gets hold of exactly the same token that was actually issued to client 1, the API gateway, again, can only verify the signature, the expiration date, maybe some scopes of the token, and will send the token to the API, even though that token doesn't belong to client 2. Client 2 shouldn't be using this token. And this is different with sender constraint tokens. So now when client 1 is issued an access token by the authorization server, the server also puts some information in the token that allows the API gateway and the API verify whether that client was allowed to use that token. So now the client, when it calls the API, it has to also present some proof of possession of that access token. And only when that's valid, and also the expiration date and signature and so on, the API gateway can pass the token to the API, and the API can verify it again. So now when client 2 gets hold of the same access token that belonged to client 1, it can't present the proof of client 1, so it presents its own proof of possession, and the API gateway or the API can reject such token because it doesn't belong to client 2. And obviously, if a client doesn't present any proof of possession, the API gateway or the API can reject the token as well. When you work with auth, there are actually two specifications that allow you to implement sender constraint tokens. So one has a really long name, auth2 mutual TLS, client authentication and certificate-bound access tokens. That's RFC 8705. And the other one is called auth2 demonstrating proof of possession. That's RFC 9449. The second specification you can use when in your solution you're not able to use MTLS. If you have clients that connect to the authorization server using MTLS, then you will usually use the first one. If you're not able to use MTLS, then you could use the second one. The idea is the same. It's still sender constraint tokens. The implementation details are a bit different. In the DPoP specification, you use the client has to issue a special JOT, which is called the DPoP proof. It issues it with every request. But let's have a look at how the first one is implemented. So when you have a client that is able to connect using MTLS to the authorization server, the authorization server will issue an access token and will put a CNF claim, a confirmation claim in the token that will contain a hash of to the certificate that was used in that MTLS connection. So the authorization server obviously was able to authenticate the client using that MTLS connection, got some information about the certificate used in that connection, and makes a hash of that certificate and puts it in a confirmation claim, CNF claim. And now when the client calls the API, it again has to use that same MTLS connection or the same set of keys for an MTLS connection to the API. And now, usually at the API gateway level, the gateway can verify whether that information about the certificate that is in the token matches the certificate that is used in the MTLS connection. And if that matches, it can send the token to the API. So another solution that FAPI mentions is PAR, and this one stands for Pushed Authorization Requests. And again, this is a standard. It's defined in RFC 9126. And it allows you to protect your authorization requests. So you get integrity protected, confidential integrity protected authorization requests. So what's the problem with the usual authorization request? When you have a client starting an OAuth flow, it sends a GET request to the authorization server, with a bunch of parameters in the query string. And eventually, the authorization server sends back the authorization code that the client can exchange for tokens. But the problem with these first requests is that it's not authenticated. So the authorization server is not able to verify who the client is. And also, the authorization server cannot guarantee that the parameters are okay. The server, of course, can validate the parameter values. So if it doesn't know the client ID or the scope values are not okay, it can return a 400 response to the client. But the server has no means of verifying whether someone has tampered with the parameters, because the request goes through the browser. The browser is a hostile environment, and the request is not encrypted end to end. It's not encrypted in the browser. So if you have an attacker in the browser, the attacker can change some parameters, send them to the authorization server, and the server will not know that these are not the parameters the client intended to send. Also, there's it's usually not a big issue, but the parameters can end up in browser logs, and maybe you can leak some important data about your API through that. So that can sometimes also be an issue. So how PAR works? In PAR, the client, before it starts the authorization flow, it first makes a backchannel request to the authorization server. It's an authenticated request, and it will send all the parameters from the authorization request that normally goes into the query string, and the client will now send it in the body of the request. The authorization server, of course, authenticates the client, verifies the parameter, saves them somewhere, and gives back a request ID to the client. And now the client, when it starts the usual authorization flow, the auth authorization flow, by using only that request ID sent by the authorization server. So now we have the authorization server is able to authenticate the client, so no unauthenticated calls. And because that's a backchannel request, it's encrypted end-to-end. So the authorization server knows that nobody has tampered with the parameters, and knows that an attacker hasn't changed anything in that request. And the URL limitation also is not a problem. Maybe on some weird device, you can have a device with maybe some IoT device or something like that, where the URL limitations could be a problem. So here again, it's not an issue. Also, the parameters don't end up in logs because they're in the body of a backchannel request. So again, it's not a problem. And another solution mentioned by FAPI is JARM, and it stands for Job Secured Authorization Response Mode. And if PAR was used to secure the authorization request, JARM is used to secure the authorization response. It's a specification from the OpenID Foundation. It's not in an RFC, but it's an official spec. And it gives you that protection of the authorization response. So what's the problem with the usual authorization response? Again, when the client starts an auth flow with the authorization server, either with PAR or with the classic kit, the authorization server will first authenticate the user, and eventually, when the user is authenticated, the server sends back a 302 redirect response through the browser to the client, sending the authorization code and state in the query string. And the client should get that code, verify the state, and exchange the code for a set of tokens. So what's the problem with that? First of all, the client has no means of verifying which authorization server issued this response. This is sometimes even a problem with some genuine communication. There are clients, especially in the health sector, that use many different authorization servers to authenticate the user. So the problem with this one is that the client gets back the code, but it doesn't know to which authorization server it should send the code to exchange it for tokens. The authorization server is able to send an ISS query parameter with a response so that the client knows which authorization server supposedly issued the token. But again, these parameters are not integrity protected. So if you have an attacker in the browser, the attacker can tamper with the parameters and change some values. And again, the client is not able to verify whether these are actually the parameters that the authorization server issued. So what happens when the authorization server uses JARM? Now, instead of sending the parameters directly in the query string, the authorization server will send a JOT in the query string, and the client receives the JOT. The client can validate the signature of the JOT and then decode it to get all the parameters from the payload. So now the client knows that which authorization server issued the parameters, and know that the parameters haven't been tampered with. The parameters are integrity protected through that JOT signature, and the client knows that for sure they were issued by this authorization server, and these are the correct values. So now we have an integrity protected response, and the parameters are strongly coupled. So again, the client knows that nobody has changed anything, injected a different value to perform some attack on the response, and it's probably the most important part is protects from the mix-up attacks, where the client would send the authorization code to a different authorization server that it should, because if it sends it to an attacker authorization server, then the attacker is able to exchange the code for a set of tokens. In fact, the second version of FAPI now recommends using the PIXI extensions. That's the proof key for code exchange extension of auth. And if you use PIXI and don't use the hybrid flow, then you're pretty much safe from the mix-up attacks on your authorization response. But you can still use JARM if you think that that's something that gives you some even better levels of protection. So some key takeaways from this talk. I think there are two most important things here. First of all, have a look at FAPI, the FAPI2 security profile document. It's not a long document, and it gives you some good advice on how you should use auth and OpenID Connect which configuration options you should use, which extensions you should use to make your solutions more secure. It doesn't matter which industry you're in, have a look at it because it might help you. And another thing is remember that when you want to protect your API, protecting the access token is an important part of that API security. One thing is making sure that no one can steal the access token and reuse it against your API. Another thing is protecting the flows which you use to obtain the tokens in the first place, because that's also important. And this is also a vector of attack where the attacker is able to get a hold of a legitimate access token and then call your APIs. So that's it from me. Thanks for listening. If you want to read more about API security and designing tokens and access tokens, especially in the cloud native space, recently my colleagues and I have wrote a book about it. It's still not published. It will be published around March 25, but you can get an early release access. It's actually free access to the book while it's still not published if you follow the link from the QR code.